Hello, I wanted to go over some of the velocity versus time and position versus time graphs, some examples so that you will have a better understanding. So I printed up this worksheet and I want to go through a few questions with you. After you watch this, feel free to ask me questions on it and I will explain it to you the best I can. So this is a position versus time graph. I want you to imagine a number line, an X number line, and at 0 seconds it is on 0. At 1 second, it's now on 2. At 2 seconds, it's on 2.5. At 3 seconds, it's on 3. At 4 seconds, it's on 3.5. And at 5 seconds, it's on 4. Now we can use this to find velocities. So, what is the velocity from 0 to 1 second? Well, velocity is going to be meters per second. And when we find meters per second, we're actually finding the slope. Because slope is rise over run, slope is y over x. So since slope is y over x, and y happens to be position, which is in meters, and x is time, which is in seconds, we could see if we do y over x or position over time, we will end up with the meters per second that we want. So for this section, what is the rise and run? What is the slope? We're going to go 2 meters in 1 second of time. So for this portion, we are going 2 meters per second. And then for this portion, we're going from here to here. So we're going 2 meters in 1, 2, 3, 4 seconds of time. So 2 meters in 4 seconds. 2 divided by 4 is 1/2. Or right here. So from here to here, we're going 1/2 of a meter per second. So this is the position over time graph. This is the object moving. And then this is what the velocity is looking like at each part. Now let's find the average speed and average velocity for the entire 5-second trip. This is a little bit tricky. Well, it's not as bad as it seems. So normally when you take the average, you add them up and divide by 2. So can you simply add 2 plus 1/2 and divide that by 2 to get the average? And the answer there is no. We cannot do that because we didn't go equal amounts of time. We went 2 meters per second for only 1 second. We went 1/2 a meter per second for 5 seconds. So we actually have to take that into consideration. So we can do it based on this graph. There's a few different ways to do that. I'll show you the tougher method first. So we're going to go 2 miles per hour for 1 second. Meters per second, excuse me, plus 1/2 a meter per second for 4 seconds. And that is equal to 2 times 1 is 2. 1/2 times 4 is 2, or 4. And we did that. This whole thing happened for a total of 5 seconds. So 4/5, or 0.8 meters per second, because it happened over a period of 5 seconds. So that was the 1 plus 4 that we did right here. Another way you can do that is, and in this case, the average speed and the average velocity are the same because they're all positive. Speed is only positive values. Velocity has direction, so there will be positive and negatives. It's positive when we're moving to the right, and it's negative when we move to the left. So since we don't have any negatives, we don't have to worry about that. The slope never went downward. The slope was never negative. So they will be the same. Let me show you the easiest way to actually calculate this. If we're doing the whole trip, we can figure out the average velocity on the position versus time graph if we go directly from the start to the end. So we're going to find the slope of the entire graph. So we're traveling 1, 2, 3, 4 meters in 1, 2, 3, 4, 5 seconds. So 4 meters in 5 seconds gives us an average velocity of 0.8 meters per second. And that's over the entire 5-second trip. Okay, we're going to try another question, similar but with some differences, but the same idea here. Let's take a look at this one. So, same questions, but the difference here is that we're going in one direction. When the graph goes downward, that means we turn around and go in another direction. So think of a number line. We're going in this direction at a certain velocity, and then we're going to go in this direction at a different velocity. So first off, let's do the slopes. This is 2 meters over 2 seconds. So that's 2 divided by 2, or 1 meter per second for that first portion, positive 1. And then here we're going down 4 over 2 seconds. So that's 4 over 2. And it's negative. So that is 2. But this is going to be negative 2 because it's down 4 over 2, negative 2 meters per second. And that we're getting right here, negative 2, for 3 seconds. I'm sorry, for only 2 seconds. That third second, that last one, it's off the graph. The graph is over. Okay, so for 2 seconds, we're going 1 meter per second. For 2 more seconds, we're going negative 2 meters per second. And with velocities, the positive negative means that they're going in opposite directions. All right, in this case, the average velocity for the entire trip, because these segments are equal, we could actually just add them up and divide by 2. So we went 1 meter per second for 2 seconds and negative 2 meters per second for 2 seconds. So we can do this. 1 plus negative 2 divided by 2. That's going to be negative 1 over 2, or negative 0.5. And that is the average velocity. And how else can we do that? We can look at the position time graph and go straight from start to finish. And we would see down 2 over 4, that's negative 2 over 4, or negative 1/2 meters per second, which is where we're getting the negative 0.5. So you can also do it that way. Now, the speed is going to be different in this case because there's a positive velocity and a negative velocity. In the case of speed, everything's considered positive because the direction doesn't matter. So here we're going to add 1 meter per second plus 2 meters per second because we don't care about the negative 2. We're going to divide that by 2, so that's going to be 3 meters per second over 2, or 1.5 meters per second. And this is the average speed. So when the signs are different, the average speed and the average velocity will differ. Because velocity, the signs, the positive and negatives, are basically telling you direction. And velocity takes direction into consideration where speed doesn't. This one, the previous question, was the same because the sign, these were all positive. So it didn't make a difference. That's why the speed and velocity were the same on each one. Okay, now I want to look at these questions, which refer back to the 2 questions I just completed. So for many graphs, both the slope of the plot and the area between the plot also have physical meanings. What does the slope of a position time graph tell you about the motion of an object? So I'm going to go back to this. The slope of a position time graph, remember slope is y over x, so position y is m and x is s. So y over x is position over time, or meters per second. So the slope of a position time graph will give you a velocity. And we do that based on the units. That, I think, is pretty easy to understand. Now, this is a little bit trickier. Looking at the velocity time graphs, question 3 and 4, determine the units for a square of area on the graph. So let me pull this here. What is 1 square of area equal to on this graph? Now I want you to think about how to get area. So area of a square is equal to length times width. Well, the length of this is meters per second, and the width of this is seconds. So what is meters per second times seconds? The seconds cancel, excuse me. So the area, which is length times width of the box, is going to give us units of meters. And units of meters mean that the area must be displacement or distance. But since we're talking about direction, it is displacement. So we could actually count these boxes and figure out how far the motion was. What was the displacement? And look, this is 1 meter, 1 meter, a half meter, because this is half the box, a half meter, a half meter, a half meter. And 1 plus 1 is 2, plus a half, plus a half, plus a half, plus a half is 4 meters displacement. But we already knew that because look at the position graph. We went from here to here, so our total displacement was 1, 2, 3, 4 meters. But this area technique is another way to see that. So the units for square of area under the graph the units are going to be meters per second times seconds or meters. And what quantity does the area under the velocity time graph tell you about the motion of the object? The quantity that it tells you is displacement. The quantity that it tells you is displacement. I want to go back to this question and find the displacement by using this technique where we use the boxes. So this is 1 meter in this box, 1 meter. Now because these boxes are under the x-axis, this is negative 1 meter, negative 1 meter, negative 1 meter, negative 1 meter. So this is 2 plus negative 4, or negative 2 meters is the displacement. Now how else could we have seen that? If we go back to the original question, the position time graph, we started at 2 and we went back to 0 as far as the position goes. We went from here to 0. That is negative 2 meters. So hopefully you're seeing how the position time graph relates to the velocity time graph. Here is one more sample. I want you to pause the video and try these questions out. I'm going to also do them and then we can check our answers at the end. Okay, so I did the position versus time graph. You see 2 meters per second where it's flat 0, 3, 0, and then this is negative 5. And then I marked those on the velocity versus time graph below. Now I'm going to answer these two questions. What is this displacement from 3 seconds to 5 seconds using the second graph? So here's 3 seconds, here's 5 seconds, here's the displacement right here. It's this rectangle. Length times width of this rectangle. Length is 2, width is 3. That is going to be 6 meters as a displacement. And I can check that here. On this graph, I went from 4 to 10 from 3 to 5 seconds. And going from 4 to 10 is a displacement of 6. It changes by 6 meters. Determine the displacement from 7 to 9. Here's 7, and here's 9. And now this is a negative velocity region. So technically this means that we are traveling in the opposite direction. Therefore the velocity is negative, as is the displacement. So this is 2 units by 5 units, which is a total of 10. Because it's below the x-axis, it is negative 10 meters. And if we did that here, we go from 10 to 0, which we can see is negative 10 meters. Thank you very much, everyone.